Hi, everybody. Welcome to my presentation, Beyond the State Machine. Wait for maybe a few minutes. Okay, cool. I'm going to go. Hi, guys. Thank you for thank you for having me here for this presentation, Beyond the State Machine. My name is Tim Streeter. I'm a senior systems integrator for software systems. I was originally, until very recently, from New Zealand, but now I'm based in Melbourne. I've been working for LabVIEW for a very long time. I'm a certified LabVIEW architect, a certified LabVIEW developer. I love LabVIEW object-oriented programming, and I have other hobbies, electronics, audio, that sort of stuff. Okay, going to start with a bit of a story. I used to work for Rocket Lab in New Zealand. My job was, I worked for ground systems engineering, doing the control systems for the launch pad, the rocket launch pad. The first version of the launch pad was written in LabVIEW, running on a Rio, and then I came along and architected and implemented the next two versions and of launch pads. These three launch pads, two in New Zealand and one in Virginia. But there's other bits and pieces I was developing as well. But and I started developing the control logic, and I got buried in case structure, how implementing the typical LabVIEW state machine. So in frustration, I Googled what is better than a state machine, and the top result was behavior trees. Okay, but what is a behavior tree? Then find out that a behavior tree is a type of a directed decision tree used for modeling control logic. I'm just going to read this out. Execution starts at the root node, follows the structure from the top, the root up there, starts following down, traversing the child nodes. Behavior trees are used in robotics, AI, and automation to implement a hierarchical top-down control. But this is typically an example of what you'll find online, because typically they're used in gaming. And I kind of figured, well, if it's good for gaming, it can do the complexity of controlling a non-playable character, then I think we can do what we need to do to control a launchpad. So anyway, here's a more relevant example, because we're not really gamers or writing games, or maybe some of us are. So simple test sequencer. It has three tests. Pretty much it waits for the logic is it waits for a start button, runs through these tests. If they pass, it runs a pass state node. If it fails, it runs a fail node. But how does all this work? What do all these mean? So each block in a behavior tree is called a node. The parent nodes are above, the child nodes are underneath. Each node can return one of three result states: a succeed, failure, or running. There are three basic types of nodes: a composite, decorators, and leaves. For composite nodes, these have one parent and multiple children. These typically control the flow of logic and behavior by managing the child nodes. There are three main types: the sequence or sequencer executes each step in order, stops if any one of them fails, and only succeeds if all children succeed. So kind of like an and. A selector steps through each child node in order, stops if the child succeeds, fails only if all children fail. It's a bit like an or. So they anyone has to pass before it passes or it succeeds. Parallel executes all child simultaneously. Success and failure depends on custom thresholds like how many has succeeded, how many failed, all failed or succeed, any failed, any succeed. Then there's decorators. Decorators, one parent with one child. Decorator nodes are used to modify or control the behavior of a single child node. They adjust how results are interpreted or how often actions are repeated. These are some typical commonly used decorators. This one's a repeater. It keeps repeating the child node until a specific fail, pass or fail condition. Then a succeeder, which forces the result of a child node to succeed regardless of the original state. Failure does the opposite, as with this, and not inverts the result of the child node. Then leaves. These are the ones that do all the real work. Leaf nodes, one parent and no children. Leaf nodes are the endpoints of a behavior tree. They perform actions or evaluate conditions. Some of the examples that we'll probably see here. These got the log node for logging messages. A wait for just adds a break in the execution. Test value performs a test on any value to make it let the logic make a decision. Assign value sets a variable to value or another variable. So let's have a look at our simple test sequencer again. So at the top, we got a repeater. It's, in this case, I haven't explicitly set it, but this one's got repeat forever. Otherwise, the logic will just stop. This one's a sequencer. So the first thing it's going to do is run this node, which is called wait for start. So it's not going to step through until the next step until it succeeds. So once it's got the logic for start or true, it's actually and succeeds, it's going to move to the next step, which is a selector. Selector is going to try and run the first node, but it will only run to the second node if that one returns a failure. But this one immediately starts test one. This is a sequencer again. So it's going to run test one. If that succeeds, it will run test two. If it succeeds, it runs test three. And so on. If they all succeed, then it runs pass. But if any one of these fails, this will return back up to the selector. The selector will then step to the next step, which is fail, and not run the pass step. Sometimes selectors are called failovers. Um, it depends how you really want to think of it. Does it fail over the logic, or is it selecting different logic? So, uh, but what this will look like in LabVIEW? This is actually a snip from a. I rebuilt this example in LabVIEW. It looks kind of like what we just saw, except it's like rotated 90 degrees. Um, but it's pretty much, I tried to make the icons look similar, and we've got um, to follow the kind of the logic. So this, as you can see, and you can actually see the advantage of doing this in LabVIEW versus text-based languages, which usually require an external editor. The LabVIEW version is actually self-describing. The code, LabVIEW code, actually forms the behavior tree, so it becomes self-documenting. Um, and like I say, it's a graphing language written in a graphing language. If you want to call a behavior tree a graphing language, kind of meta, really. Did I miss the step? One thing I should point out, these ones here are actually um, sub trees. They're actually called subtrees are called branches. So this is like a wrapped up VI containing um, more of these leaves and composites and decorators. And they're all wrapped up. So that kind of tidies up into a modular way, like of describing what I want each thing to do. without actually exposing the complexities of what each thing does. But each thing does have more, and we'll get to that. Shall we have a look at the example for the test sequencer? All right. Get to the right example. All right. Okay. Bit of a complicated front panel because I've actually got some simulated data running. We'll have some simulated data, and I'll just skip over a bit of this, and this will actually use the behavior tree. Each of these are, you got your repeater set to run for never, but you have other options there. This sequencer, which will step through these, got wait for button, which has got more complicated logic in it. It has to check that it makes sure it's in a fail state before it runs, checks it's in this succeed state. But let's see it running. So I'm actually just generating some sine waves at a specific frequency, specific amplitude, and then I've got just a random noise generator with a bit of a DC offset. So if I hit start test, it will actually just quickly run through the test and report the values. The most standard feature I find useful in debugging stuff is have logging, which I think you need for any complicated programming stuff, and that will fail. Um, yeah, that's a implementation of a test sequencer written as a behavior tree, and I think it looks kind of useful. I mean, and then the representation are easily to scale and easy to be. Here's my logging message. This is where I assign values, and this is a sequencer, and all this is just IO references getting passed in. And I this is actually this is the engine gets created here. The engine started here. The engine stops here. Engine is cleaned up, closed. All this here is just IO. So it's really just mainly just preventing it going straight to stop, because you can hit the stop and immediately kill execution at any time. But you could just have a loop in here. You can actually check the final status. If the final status is quit, it just quits. But yeah, I've had some people confused that this behavior tree isn't executing all the time. It is just run through the once to create this final class, and that class is executed, and that's all there is. And this creates an actor, which launches off and starts running this. Cool. Let's go back to the presentation. Okay, next. So how does this compare to a state machine? Because this is where I'm actually trying to move from. So why do we think this is a better than actually a behavior tree is better than a a, a state machine, a typical case-based state machine? And this is when I started to put together some pros and cons. Behavior trees are self-documenting, like I pointed out before. They scale. You can actually build up modules on top of modules on top of modules to scale out how your code does, insert additional codes, especially if you've actually created your branches in a nice intuitive way, and then the whole thing becomes intuitive. They're modular because each part can be tested individually without having the whole system together. You can actually say, the bit like the step I have for the uh, wait for button, it can be tested by itself. It won't do very much, but you can. That's how I developed it. I tested it by itself first. That's why I found out a bug, which I added, made the code a lot more complicated than it needs. It looks like it needs to be. Reactive. Um, Interesting statement. It's more of the design being a reactive design. And then it's also built from a small set of simple parts. Like what you saw there seemed complicated, but mainly there wasn't any new bits in there, just making sub VIs out of parts, but out of modules, but out of smaller modules to create a bigger module, bigger trees, branches, I should say. But then, of course, the cons: high initial overhead, high initial, um, high VI count. There's lots of VIs underneath, mainly because there's lots of abstraction going on, and object-oriented programming. And you've got to learn how the behavior tree works, which is not quite always as intuitive as you would think, but once you get it, it's not too bad. And the pros and cons of state machines. It's standard for this type of, they call it task switching structures, where you're actually trying to control logic. The code's fairly light. I mean, it doesn't take very long for a state machine to load, and we'll see that in a second. And everybody knows what it is. But my cons, what I don't like about it, and I've kind of never really been so comfortable, because everybody hates the sequence structure, but the original stack sequence structure. But really, a case structure has all the same issues. You're kind of hiding all your code, um, and you have to look through them to see what it's doing. And then, unless if it gets really deep, it's like you're trying to memorize a lot of stuff so you know where you're going. And essentially, you're making a go-to. You're jumping around stuff without a clear return path. I mean, you could return to a different location. You'd have to, yeah, I don't like it. It's not modular, not really. It's not easy to move things around once you've written it. You've got to kind of have a plan and state in place to get it to go correctly. And it's not easy to reuse that state. I mean, you could try switching to that state if you think you're going to use it again, but you have to jump back to a different location. That means you've got to have a case around it. You're going to make these decisions. Gets kind of messy. I mean, you could implement a hierarchical state machines, but then that's another level of complexity again. And it's straight out difficult to scale, because once you get to be, I don't know, complicated, if it was just running in order, kind of like a replacement of, you could have them mini deep because only running in order. But once you're switching around, stepping this and back and forwards, then at a certain point, you're not really going to know what's going on unless you kind of slowly debug through all the case, and unless you had it completely planned out at the beginning. And, unless you've got that documentation there, you're really going to struggle in the future. Okay, demo two. This is where we're going to actually compare. Let's close this one. So I needed something. I need a state machine that moderately complicated. Um, but I could easily get. I didn't want to waste too much time creating a really complicated one unless somebody has. And because I also have to. The idea was I'm actually going to implement this again, and I have implemented this again in a behavior tree. I don't want something that's kept me too much time, but this one has got quite a lot of. This is actually from a LabVIEW developer solution called it's a solution code for one of the LabVIEW developer exams. Um, and essentially, you choose what you want it to do, hit start. This is your car simulator. It's currently entered. It moves to the first position. It starts running an automated sequence, doing of each that you've selected each stage, so on and so forth. And it's actually, like has all these cases. I mean, it's not super complicated, and it hasn't been implemented at the bare minimum. And they're kind of using instead of a queue, they're using an array of cases. Like trying to change your. Um, it's nice having documenting enums, but then to change one, and all the order changes. So this is how I would have implemented it in behavior tree. Use the same front. Same same original front panel, except I added logging messages because they're great and it helped me debug it, and also to see how things are going. Do the same thing to start, start. There we go. Move that position, waiting, next position. Some details of what's going, all the different stages it's gone through. I think that's a little bit more than what this one does. So this one looks very similar, the same kind of concepts, allocating IO up front, behavior tree next, pass it into the execution engine started, start executing this the behavior tree, populate some IO so we can see what's going on, hit stop and close once you hit the stop button. And the behavior tree for this is that, which is a lot simpler than that, if you'd ask me. I can see what's going on. First, I have to reset the indicators, start a message chain, start. Then I'm just waiting for a start button, wait for a card to enter. Then once it's got to station one, do whatever station one does, station two, station three, then exit. I mean, there's more to it, and each one is that. Each one is like waiting for car at station one. I've reused this. This is another branch. It's waiting for station number one. So once car gets into station number one, it's going to sit there waiting and then log the message. Set some IO on the front panel, do the underbody wash, and so on and so forth. All right, so I think I've covered quite a lot of stuff in a very short period of time, in only 20 minutes. Has anybody got any questions? Would anybody like to see anything else before I continue? I have more slides, but not a lot more. Quietness. It is a fairly new concept. Um, yeah, okay, going back. Essentially, it only goes forward until it depends. Let's bring this one up. So this is actually just going to run forward until one of these fails because this is a sequence. Then the repeater here will go, it's set to run for repeat forever, so it doesn't care. Um, and then it's actually just going to go back to the beginning and wait for start button. Share a project example. So you want to see underneath. Back for Dier's comments, it's kind of like you've got to typically think like if you need to do something happen to station one before it hits to station two, you'd have to add some like if this one fails for some reason, which I know it won't, but if I run the selector, if that fails, then we can have some fallback logic that does something else and we could have a repeater that could let us retry. And this will then, so when it repeat until succeeds, um, there is a version that repeats until timeout as well, so that one you could actually keep trying until something runs out of time. You give it a certain threshold, so it has a quit status, and then it returns fail. And then maybe this one here will like, oh, you failed somewhere, so we'll actually do some fail logic to make that one fail. To handle run alarm, let operator know, they reset the system, goes back to beginning. It's possible to share the project example in order to learn how it does it work. Um, so they are available. I'll talk about that in a bit. But what I might do, I might. How much time do I still have? I haven't even done a half an hour yet. Um, I'm going to do couple of simple things. I'm going to show you how it's modular. Typically, you shouldn't do this sort of stuff because it's always going to fail. I'm going to test wait for button. So I'm actually just going to scrap all that. I'm going to stick pass in there because I need some. Wait for button doesn't actually give any feedback, but pass does. So this one here is actually just going to sit there and wait for the button and run pass. And wait for the start button. There you go. And repeats. Simple programming. And to understand, maybe I'll go over what a custom step involves, because these are actually these are actually built up of 9 bits. This is all just out of the palette set that of the decorators composites. Where is the? Oh, it's off the side. That's why I'm not used to having such a small. I've resized the thing screen to be smaller. So I'm actually going to make a step from scratch as part of the test sequencer, so you can actually see what's involved in making a step. So I'm actually going to just go create a. So this has already got some custom nodes, so I'm going to make a new one, new class. So each of the nodes are actually in fact, we want a leaf. What do you want it? Dialogue. Message. So they all have to essentially each of them, each step is made. Each of these nodes is made out of is based on a class which has to have at least the execute step. But you can have a cleanup initialize. When you start the execution engine, it runs initialize. When you run the close, it runs a cleanup. But execute is if you don't need to anything. Execute is run when it gets to the step. So we want it to only return success or the status. In this case, we just want success because we're not going to actually do any logic. It's just going to always return success. And all this is going to do is We're going to throw in a one-bar dialog because we just wanted something to indicate pass fail. Need a message. And yeah, all right. Now I'm just going to drop that. New custom leaf. Yes, I need to be quicker. Gets into shortcuts. I don't know why I never. Yay. Oh, I deleted the message anyway. Duh. I think I just passed and yeah. Yeah. Anyway, you get the idea. That's how you create. I mean, it's a lot of classes, but you get quick at building classes. Hopefully, that's a good enough example of how it all kind of works underneath. Yeah, essentially, each of them is just um, classes. Just the trick is is actually working with this known set is the logic and building up to make things work as they do. All right, back to the. Any other questions before I continue? I will have some more questions at the end if you want. Okay, let's resume. Okay, so where are these used? Um, they came from non-gaming. Halo 2 specifically was the first uh, system to use behavior trees as far as history can tell. I think there was, it, it came from others. It might have been a lead on from something else, but that's when it's well known. And so in gaming, it was used for the non-playable characters to describe like deep behaviors that have like, have anybody thought about what, those non-playable characters, how do they decide what they're going to do at any given time? Um, and behavior trees is one of the most common ways. like deep decision making through these things were done, like go to door, go to next door, go to room, go through all doors in room. Um, and then also like strategy game control, like strategy games where somebody makes a decision which leads you down to a different path. Stuff like that's perfectly can be perfectly described by have a behavior tree. Pretty large language models, autonomous vehicles were controlled by behavior trees because they've been around for the reference I found was 2017 when they were using. Obviously, didn't really take off because not until large language modules came about that autonomous vehicles became particularly useful. Um, Drone control, industrial robotics, and also robotic swarms. A lot of research articles on this stuff. Um, but what I think they could be used for, like test sequences, car wash controllers, a PLC ladder logic alternative for your Rios. I mean, a lot of the stuff I ran on PLCs and Rios for Rocket Lab, back off controllers or, uh, yeah, real time controllers. Application logic, like if you controlling the general flow of your decision making of, like if you many decisions have to be done. I don't know. It's kind of like, and any other, but pretty much complicated test and task switch. I mean, there is a certain amount of overhead involved. You got to. I mean, I've written a lot of the code and to do stuff, but you still got to set up a few things. And I made a template which made even building the simple stuff getting easier. But you got to. Originally, you'd have to all that code you saw would have to be written, where it'll be a lot quicker to write a state machine sometimes. Okay. Um, so how can you try it out? So I actually got this code's open sourced. I mean, I'm writing a lot of stuff. Here's the link to the behavior tree. I mean, the behavior tree, yeah, behavior tree open source code. I created a template for it that makes life a lot easier. Just about because the basic stuff pretty much stays the same. It's just growing your tree, choosing your IO. That's the bit that's going to take time. You can scale it. Um, I've got examples. Um, there's steps through. They've got these ones that I've seen are actually mostly all there. Um, a test sequencer, car wash, as well as these other basic ones that show you how to implement each one of these. And then they're also available on the VI package manager, of course, from 2021 LabVIEW, because that was and it's open source because I originally was doing this in my spare time using the community version, which is all cool because I really wanted this to be available for. I thought other people would find this useful, and I don't want it to be lost after after I left Rocket Lab. This is not Rocket Lab's code. This is all mine from scratch, rewritten from scratch. And also, do you want to learn more about behavior trees? It's not like I've made something up from scratch. This first link is actually from Chris Simpson and a game developer on how they describe how you can use behavior trees. And that's really where I got my head around how the whole thing was going to work. Um, and then I found this really good small book thesis. I think um, it's from the Cornell University. It's archived at Cornell University. It goes through lots of details. It's really interesting. Those two links there, if you're interested. Oh yeah, you can actually just point your camera at these, and they work. Uh, I did this at NI, the GDevCon Australia, New Zealand, ANZ, and yeah, everybody was putting these up. It works really well just to get camera at it. Um, and yeah, any more questions? got 10 more minutes. I'm too quick. Does anybody want me to dig into further into my examples? Okay. Yeah, and that's all I have. Thank you for taking time to watching my presentation. I hope this um, hopefully this opens some ideas for you guys. And if you have any questions, my email address is here, tim.streeter@software systems. Um, I'm in Melbourne, but the main company's in Sydney. If you have any questions about this, just drop me an email. Thank you, guys.